Assalamualaikum and hi. We continue Mechanics of Materials, Chapter 4. Previously, you already learned Chapter 1, which is Analysis of Stress. Chapter 2 is Analysis of Strain. Chapter 3 is the Mechanical Behavior of Material. And now Chapter 4 is the AXIAL load. Chapter 4 is a combination or the relationship between Chapter 1, Analysis of Stress, Chapter 2, Analysis of Strain, and Chapter 3, Mechanical Behavior. Here in Chapter 4, we would like to see the relationship between all these stresses and strain that happen to the structure that you analyze. Chapter 4 is the AXIAL load. AXIAL load is the load that had been applied to the structure. In this chapter, we would like to see the displacement occurred due to the applied load. Let's take a look at the learning outcome. By the end of this chapter, you should be able to define the elastic deformation of an axially loaded prismatic bar, define the multiple prismatic bars, define the principle of superposition, define the Simon principle, calculate the deformations of member under axial load, calculate the deformation of member for stepped composite bar, analyze the deformation in systems of axially loaded bars, analyze the deformation of member for statically indeterminate assemblies, calculate the deformation of member due to a temperature effect. So basically in this chapter, we will calculate the deformation and also the displacement of the structure. As for introduction, in Chapter 1, the concept of stress was developed as a means of measuring the force distribution within a body. In Chapter 2, the concept of strain was introduced to describe the deformation produced in a body. Chapter 3 discussed the behavior of typical engineering materials and how this behavior can be idealized by equations that relate stress and strain. In this chapter, discuss two general approaches used to investigate a wide variety of structural members subjected to axial loading and also the deformation. So as I mentioned earlier, we already learned the concept of stress. You know that stress is equal to P over A, which is force divided by area. You have two types of stress, which is normal stress and shear stress. For normal stress, symbol is sigma. For shear stress, the symbol is tau. And for strain, we already learned to calculate the deformation. Then for strain also, you have two types of strain. You have normal strain and also shear strain. For normal strain, the displacement divided by original line. For shear strain is a change of angle, so you need to calculate the angle. And Chapter 3, we discuss the behavior of the material after we apply a tensile load. When you apply the tensile load, you produce a stress and strain diagram. For stress and strain diagram, they will give you modulus of elasticity value and also modulus of rigidity value from shear stress and shear strain diagram. And from here, you know the behavior and you know the properties of the material. And in Chapter 4, we would like to calculate or we would like to analyze the members subjected to axial loading and also the deformation. Simon principle. Simon principle states that both localized deformation and stress tend to even out at a sufficient distance removed from this region. For example, this is your structure. Here is your structure. And then you cut at AA, you cut at BB, and you cut at CC. Here is your applied load. And then when you cut the segment at AA, you can see the distribution of stress. But as it moves to the center, for example, this is your center. As it is close to the center, then you can see that the stress distribution here tend to even out, mean tend to distributed well. So that's why in everything, in each stress, which is shear stress and normal stress, we calculate the average stress. Then you have the average stress is equal to P over A. Elastic deformation of an axially loaded member. Using Hooke's law and the definition of stress and strain, we are able to develop the elastic deformation for a member subjected to axial loads. Suppose an element subjected to a load, then you have stress is equal to P over A for normal stress, and normal strain is the displacement divided by original length. When you integrate this, you will get this formula, which is this is a displacement. And then mathematically, it can express that displacement is equal to P L over AE. P here is a load, O is a force, L is a length, A is a area, and E is a modulus of elasticity that you get from stress-strain diagram. When a constant external force is applied at each end of the member, then you can have the displacement here. For example, when you stretch the bar, then it becomes deformed. When it's deformed, it has some displacement. For example, a rubber band. Rubber band, when you pull, you give a force to the rubber band, then it becomes elongates. The displacement or the change in length, final length minus original length, is the displacement that we would like to calculate. Remember back the sign convention that you had in chapter 1, where you have the internal resultant forces. You have the force acting if you take from left hand side, all the internal forces should be positive to the right. If you take from right here, then the internal forces should be to the left, positive. Sign convention you need to remember until year 4 in structural subject. So please remember the sign convention if you take from left here or if you take from right. You can take either way if the question did not give you the direction of section. But if the question gave you the direction of section, then you need to follow the direction. Let's take a look at example 4.1. The uniform A36 steel bar in figure has a diameter of 50 mm and is subjected to the loading shown. Determine the displacement at D and the displacement of point B relative to C. A36 steel, if you look at the table of properties, then you will get the E value, which is a modulus of elasticity value. From the properties table, E value is equal to 200 gigapascal. And the question gives you the diameter. Take out the information given. Diameter is equal to 50 millimeters. And the question asks you to calculate the displacement at D and also the displacement of point B relative to C. Here at A is fixed, B you have 80 kN applied load, at C 40 kN applied load, and at D 70 kN applied load. A is fixed, so you need to start from free end. You cannot start from the support point. You need to start from free end. This is free end, and this is fixed supported. So you need to cut between CD, between BC, and between AB. What you calculate, you need to calculate the internal forces. Remember, we did not calculate the applied load. Applied load is not equilibrium. The internal load that had been applied to the structure is in equilibrium state. Okay, please remember. First, you calculate the area. Area of the bar, since they gave you the diameter, is equal to 50 millimeters, so I convert it into meter. 0.05 meter. Then you have, this is a bar, then it is circle. Pi d square divided by 4 is equal to pi times 0.05 square divided by 4. This one is equal to please put the units, and then after that we would like to calculate the displacement at D. Here if you look at the diagram, the D is the last point of the bar. So the displacement at D, for example, this is the displacement at D, is subjected to segment AB, subjected to segment BC, and subjected to segment CD. Okay, because it is at the last point, it subjected to the first point until last point. And then the displacement at D is equal to this displacement at section AB plus BC plus CD. Okay, remember you need to cut the segment. Section the segment. Remember the sign convention, because A is a feet supported, then we should start from right. So everything should go to the left is positive for internal loading. Segment CD. Segment CD, you have 70 kN applied load. Then you cut here, then you will expose the internal force, which is, I name it as a NCD. Then by using equilibrium equation, summation Fx is equal to 0, to the right is positive, then you have negative NCD minus 70 is equal to 0. NCD is equal to negative 70 kN. Segment BC. Remember, it should be in equilibrium, so you cut from D to between BC. So here at point D, you have 70 kN applied load, and then at point C, you have 40 kN applied load. Then when you cut, you will expose the internal forces. This one, I name it as a NBC. Again, summation Fx is equal to 0, to the right is positive. Then you have, please do the calculation. Then NBC is equal to negative 30 kN. And you do the same for segment CD. Start with point D, C and B, and then your internal load and CD. This one you will get NCD is equal to 50 kN. Displacement at D is equal to displacement AB plus displacement BC plus displacement CD. Then you have the formula, displacement is equal to PL over AE. P is the internal forces, at each segment. L, here is the length of each segment. And A, area of each segment. If your bar have different diameters. And E, here is the modulus of elasticity of each segment. if your material is made by composite material, which is the different materials. Then we calculate for AB. P for AB is equal to 50 times 10 power of 3, remember kilo power of 3, times 2 meters, the distance or the length of segment AB. Area we already calculated earlier, 1.963 times 10 negative 3, and MOE, modulus of elasticity, is equal to 200 times 10 power of 9. Then you get the answer. And then segment BC, negative 30 times 10 power of 3, because it is internal force, you need to take the negative sign. The length is 1 meter, divided by area. Then you will get the answer for each segment, displacement at each segment. When you calculate, you will get from here you can calculate the displacement at D. Therefore, the displacement at D is equal to, you do the calculation, then you will get negative 8.916 times 10 negative 5 meter. This is your answer. Why it is negative? Because D moved to the left. Okay, because point D is the last one, negative move to the left. And the question also asks you to calculate the displacement of point B relative to C, which is segment BC. So you just take this answer for segment BC. Please remember, the important thing here is your calculation for internal forces at each segment. Students usually they just take the applied force. Applied force, as I mentioned, is not in equilibrium state. That's why we did not consider the applied force. You need to consider the internal force. How to calculate the internal force? You need to cut the segment by following the sign convention. This sign convention is the universal sign convention, means that all engineers around the world use the same sign convention. So you need to follow. If you get negative value for the internal force, then leave it. Just like what I done here, if I take negative value, then I just substitute in the formula. Okay, and please try this one. This is same, just the unit is in Newton. Before this, the units in kilo Newton. So that's why I times 10 power of 3. Here, that's why I times 10 power of 3, because the unit given to us is kilo Newton. Now the unit is Newton, so no need to times 10 power of 3. Okay, for this question, read the equation. Determine the internal forces of each segment of the bar. Thus, calculate the displacement at E and the displacement of point C relative to D. Okay, here the missing information, the diameter of this bar is equal to 25 mm and E is equal to 200 gigapascal. The question asks you to calculate the displacement of E and also the displacement of point C related to D. Same question, because A is fixed, then you need to start from E. When you start from E, everything should go to the left is positive for internal forces. So you need to cut between ED, between CD, between BC and between AB. When you expose the internal forces, then you can calculate the displacement at each segment. Okay, the question asks you first to calculate the internal forces at each segment. So you need to cut and then follow the sign convention, you will determine the NAB, NBC, NCD and NDE. After that, you calculate the displacement at E and also the displacement of point C relative to D. And then when you calculate, you will get the answer. Please try this one. You will get the answer negative 3.2592 times 10 negative 5 meter. Negative means E move towards left. And CD is equal to negative 6.111 times 10 negative 6 meter. Let's take a look at this example. Example 4.3. The assembly consists of an aluminium tube AB having a cross-section area of 400 mm square. A steel rod having a diameter of 10 mm is attached to a rigid collar and passes through the tube. If a tensile load of 80 kN is applied to the rod, determine the displacement of the NC of the rod. Take the modulus of elasticity for steel is equal to 200 GPa and modulus of elasticity for aluminium is equal to 20 GPa. Here it consists of two types of material, which is aluminium and steel. AB is aluminium. This is aluminium. And BC is a steel. Then you need to calculate the displacement at NC. Subjected to B. Okay. This question already gave you the A. A value is equal to 400 mm square and the diameter is 10 mm for steel. This one is for aluminium and steel. P 80 kN, and you need to calculate the displacement at C. And please remember that you have two types of material, which is aluminium and steel. For this one, you have 80 kN to the right. To make it equilibrium, you need another one here is to the left, 80 kN. You can do the equation summation Fx is equal to 0, then you will get 80 kN that I put it here. Then you draw the free body diagram. First, for aluminium, segment AB, which is a aluminium. And then this is 80 kN. To make it equilibrium, you have another force here to make equilibrium here, which is I name it as PAB or PBA. This one is PAB. How to calculate PAB? Again, summation Fx is equal to 0. To the right is positive. Then you have negative 80 plus PAB is equal to 0. Then PAB is equal to 80 kN. For CB, which is for rod, steel rod, and you have small steel rod. At point C, you have 80 kN. The equilibrium force is PBC to the left. PBC is equal to 80 kN. The displacement at C is equal to same the displacement of aluminium AB plus displacement of steel BC. Then you can calculate the displacement. For AB, you already have the area for aluminium, which is 400. I convert it to meter. For steel, you can calculate, which is pi d square over 4. Then you will get your area, 7.8 times 10 negative 5 meter square. And then you can calculate the displacement at C is equal to PAB, which is we already calculated, 80 times 10 power of 3 because of kilo. And the length based on the figure is 0.4 meter divided by area, which is 400 times 10 power of negative 6, and then your E 70 times 10 power of 9 plus segment CB 80 times 10 power of 3 PCB. The length is 0.6 divided by area 7.854 times 10 negative 5. E is 200 times 10 power of 9. And then you can have the answer in meter because I use meter. If you would like to use millimeter, then you can use millimeter. Okay, you can try this one. The 20 mm diameter A36 steel rod is subjected to the axial force. Determine the displacement of NC with respect to the feed support at A. E is equal to 200 gigapascal. So the question already give you E is equal to 200 gigapascal. Here you need to cut between AB and between BC. Both are same materials and the diameter is same, which is 20 millimeter. If you would like to use millimeter, then you can use millimeter. And you need to calculate the displacement at N, C. A is feed supported, then you need to start from C. Okay, please try this one. Same procedure as what we do previously. Try this one also. The composite shaft consisting of aluminium, copper and steel sections is subjected to the loading as shown. Determine the displacement of NA with respect to ND and the normal stress in each section and the normal stress in each sections. The cross-sectional area and modulus of elasticity for each section are shown in the figure. Neglect the size of collar at B and C. This is the collar, so you can neglect this one. Composite shaft means it is made from different materials. AB is a aluminium, BC is a copper, CD is a steel. The E modulus of elasticity and area is given. Cut between AB, cut between BC and cut between CD. Here the question didn't have any support, so you can cut from A, or you can cut from D, or you can mix up. You need to calculate the displacement at NA. So the displacement at NA with respect to D is equal to displacement AB plus displacement BC plus displacement CD. And the question also asks you to calculate the normal stress at each section. Normal stress is equal to P over A. P is the internal forces. Remember, P is the internal forces. Then you need to calculate for stress AB, stress BC, and stress CD. The first thing you need to do is to cut the section and then expose the internal force. Please do this one class and then you will get the answer. The displacement AD is equal to negative 7.266 times 10 power of negative 5 meter. Okay, if you get AD correct, then your stress should be correct. We'll continue in part 2 chapter 4.